Okay. Uh-oh. Board's not working. That's a problem. Okay, there we go. All right. So we're going to do 7.3C, and then we're going to work on the practice test. And there might only be 2 chapters after this. I'll have to double check, but I think we only do 9 and 11. So anyway, we're going to have a lot of time to study for the final. The bad thing is, I don't know if there are going to be any practice finals. Anyway, we'll see. Okay. So this worksheet deals with confidence intervals of the difference between 2 samples. And in chapter 6, we did the difference between 2 proportions, and in 7, we did the difference between 2 means, and both of those are going to show up on this worksheet. Now, there are some more complicated situations that this class doesn't really cover. So as far as the means go, we're kind of doing the basic version, and anyway. So, number 1. A study compared the effectiveness of 2 different allergy medications. A was given to 200 patients and 114 reported a reduction in symptoms. B was given to 150 with 90 reporting a reduction. Construct a 95% confidence interval. So for sample 1, we had 140 out of 200. And for sample 2, we had 90 out of 150. Move my calculator over. All right, so 140 out of 200 gives us 70%. Okay, and then 90 out of 150 gives us 60%. So what is the actual difference between the two? And it tells us which way to subtract. So medication A minus medication B. So the actual difference is going to be 0.7 minus 0.6, which is 0.1. 10% difference. And remember, a confidence interval is going to take that 10% and it's going to draw a window around that 10%, and this window needs to capture 95% of the population. Now, we'll never know, but no, I said that wrong. That window has a 95% chance of capturing the true proportion, the difference between the 2 proportions. But we'll never know if we actually capture it or not. And so we need the standard errors for both of those measurements. So we need the standard error for this and the standard error for that, also known as the standard deviation of the population distribution, sampling distribution. So I'm going to take 0.7. Do you guys remember the formula? Oh, it's not 0.7, sorry. It's the square root of 0.7 times 0.3 divided by 200. And we get 3%. Okay? And then the square root of 0.6 times 0.4 divided by 150. You guys remember that back from chapter 4? Okay. So we have standard errors of 0.032 and 0.04. Now I need the standard error for the difference. Do you remember this formula? It's the Pythagorean theorem. So we're going to do the square root, maybe, square root of 0.04 squared plus 0.032 squared. And I get 0.0512. So that is my standard error. Okay. Now I want a 95% confidence interval, and when you're doing proportion, we can use the z-table. So I've given you a z-table, and, oh, that's the wrong one. It's this one. So I want a central area of 95%. So I look at the area column. 95% in the center is a z-score of 1.96, okay, which is about 2, right? So what do I do with that 1.96? Go back here. So I need to go 1.96 SEs to the right and 1.96 SEs to the left. So I'm going to take my 0.1, my 10%, plus or minus my z-score, 1.96, multiplied by my standard error for difference, which is 0.0512. Now, I did everything in decimals. You could do the same calculations in percentages after you compute these numbers. So the SEs have to be computed in decimals, but once you have that, you could do everything else in percentages. Okay, do you guys remember this? Kind of? So 0.1 plus 1.96 times 0.0512, and then I'm going to do the same calculation with a subtraction. Oh, what is that? It's negative 0.000352, which is essentially 0. So my confidence interval is from 0 to 20%. What does that mean? Any ideas? What is somewhere between 0 and 20%? The true difference between the two populations is somewhere between 0 and 20%. And we are 95% confident that that is accurate. Does that mean there's a 95% chance? No, because we're either right or we're wrong. But the process of taking two samples and doing this computation is correct 95% of the time. But once you've taken the samples, then the probability changes to either 100% or 0. You either will capture it or you won't. So we use the word confidence to let people know that this is not a probability. We used a z-score based on 95% to compute this window. Okay, what if on the next one it says a 90% confidence interval? How is that going to change that calculation? So we're going to go to our z-score table. We're going to go to 90%, which is 1.64. Okay? All right, so the first, I don't know, 4 or so are proportions. And then the next set is going to be all means. So look at number 5. A study compared the average test scores of students taught using two different methods. Group 1 had 25 students with a mean score of 82, standard deviation of 7. Method B had 30 students with a mean of 88 and a standard deviation of 5, and we're going to do A minus B. So my actual difference is going to be 82 minus 88, which is negative 6. Okay? Now I need standard errors for both of those. So the first one is going to be 7 divided by the square root of 25. And the second one is going to be 5 divided by the square root of 30. And then I'm going to take the square root of those values squared and add it together. Does that make sense to everyone? Okay. So 7 divided by the square root of 25 and 5 divided by the square root of 30. And then we will take the square root of 1.4 squared plus 0.9128 squared. And I get a standard error for difference of 1.67. Now here's where it gets a little tricky. Because we don't know the standard deviation of the population, we have to use the t-score instead of the z-score. When you're dealing with proportion, you can use the z-score because the standard deviation can be estimated accurately using the percentage from the sample. But when you're dealing with two means, the z-score is not going to be very accurate unless you have a lot of people in your sample. And we don't have a lot of people in our sample. So we can't use the z table, we have to use the t table. Now, the t table is based on how many people are in your sample. Okay, and this is going to be kind of weird, but the t table is usually the number of people in your sample minus 1. However, we have two samples. So what we do is we add the number of people in both samples and we subtract 2. And that is called the degrees of freedom. So there are actually an infinite number of t-tables. So what I've done is, I've done a really poor job printing this off, by the way. I apologize. It's going to be a pain. Hopefully Garrett printed it in a bit better manner. So on your t-table, you have degrees of freedom on the left, and then you have the area outside the two tails in the middle. All right, so what are our degrees of freedom here? So the formula is we take 25, that was the number in the first sample, plus 30, that was the number in the second sample, and we subtract 2, and that gives us 54. So we go to row 54. Now there isn't a row 54, but 54 and 55 are so, or 50 and 60 are so similar, it's not going to make much of a difference. So we'll round 54 down to 50. Okay? Now, which column are we going to use? So which column will put 95% in the middle? The numbers across the top are the areas in the tails. So if the center has 95%, how much do the tails have together? 5%. So we're going to look column 0.05 and row 50. And we get this value right here. That is our t-score. So we're going to take our actual difference, which is -6, plus or minus our t-score, 2.009, times our standard error for difference, 1.67. Does that make sense to everybody? So it's similar to the z-score, but it's just a little bit harder to make. Well, it's not harder. You just don't want an infinite number of t-tables. And if you look at the bottom of the t-table, 1,000 and infinite are practically the same, right? So if you have 1,000 people in your study, actually, maybe I should do this first. So -6 plus 2.009 times 1.67. So that's one bound, and then the other one. So we are 95% confident that the true difference between the two samples is somewhere between -2.6 and -9.3. Okay, so let's go back to that t-table. So notice if you have a lot of people in your sample, the z-score table and the t-score table are identical. And it only takes about 1,000 people, maybe 500 would be enough, before they end up being the same. So what if I wanted a 97.5% confidence interval? What column would I use? I would use this one. And what confidence level would that be? That would be 99% confidence level. What would that be? A 90% confidence interval. Okay, does that make sense? All right. I think I have the answer for the first 4, but that's as far as I made it. So I'll throw those up on the board. Okay, get to work.